So up until this point, we've looked at ionic bonding, which is the bonding when a metal gives electrons to a non-metal. So ionic bonding is the bonding between metals and non-metals. We've looked at covalent bonding, which is when two or more non-metal atoms share a pair or pairs of electrons. So that's bonding for non-metals only. And so the third type of bonding is looking at the bonding for metals only. And that one's called metallic bonding. That's what we're going to look at in this video. It says here, the structure of metals can be described as follows. A regular arrangement of positive ions surrounded by a sea of delocalized electrons. Draw in the space below a diagram that shows the structure of a metal. So we don't actually need to know a huge amount about metallic bonding, and we did diagrams showing how the bonding originates in ionic bonding and covalent bonding. Here we just need to know what the structure of a metal looks like, and it is a regular arrangement of positive ions surrounded by a sea of delocalized electrons. So let's just draw a circle there to represent a metal ion. Okay, now metals are always positively charged ions, so I'm just going to put M plus there. Now there's no element M, I'm just using that to represent a metal ion. Now it's a regular arrangement. A regular arrangement is a neat and tidy arrangement, like bricks in a wall. I'm just going to leave a little bit of space between them. Okay, and you'll see why in a moment. And the aim, what we're trying to do here is to make all these metal ions the same size, or roughly the same size. Now I'm appalling at drawing, but see if you can try and make them roughly the same size. That's a bit bigger, isn't it? It's a bit rubbish. And we'll do that many. We'll do them in nice lines. So that's a nice regular line. Now, as I said, bricks in a wall. So we're going to do the next iron up here. Again, roughly the same size if we can. Exactly the same size if we can, really. I'll settle for roughly, though. Okay, and so we're just alternating the rows. So this row here is sitting kind of in the holes created by the first row, and the next row is going to be back to in line with the first row. Again, more metal ions, please. Roughly the same size in a nice regular arrangement. And we'll do one more there. You can do as many as you want. I'm just going to do that many, and we'll do one final row. So what we've got here is all the metal lines neatly arranged in a regular arrangement. That's so. Okay, so that's the regular arrangement of positive metal ions. Okay, because metal ions are always positive. Now they're surrounded. Now you may just say, looking at this, positive, 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 positive. Don't like charges repel? Of course they do. And the other question to ask, I suppose, is, well, how did they become positively charged? Well, let's look at lithium as a nice, easiest metal to draw out. Lithium's got an atomic number of 3, which means it has 3 protons in the nucleus. Okay, which means it has 3 electrons around the outer shell. Okay, and in the element, they all balance each other out. So if this was lithium here, how's this become positively charged? Let's just remind ourselves what lithium looks like. 2 electrons on the first shell, 1 electron on the second shell. That's going to want to lose an electron from its outer shell to get a full outer shell, and that electron is lost. But where does it lose to? Well, the answer is it sits between the layers. Okay, it's like the cement that holds the bricks together in the wall. So these positive metal ions are surrounded by a sea of delocalized electrons, and these are the delocalized electrons. Sea of delocalized electrons. Now, delocalized electrons are free to move. Okay, and if you're thinking about it again, why is it positively charged? Well, it's lost this electron, so that electron there maybe is gone. Okay, so that one would cancel that electron would cancel that proton, that electron would cancel that proton, that proton is now going to be left on its own because this electron's gone, which is why that's going to become positively charged. Okay, so metals. Okay, do they have high melting points or low melting points? Well, we've got positive ion attracting negative electron, attracting positive ion. Okay, so they are strongly attracted. if they're strongly attracted, it's going to take a lot of energy to break those opposite charges from one another. So the melting points of metals are high. Let's just write that there. Melting point high, lots of energy needed to separate positive metal ions from negative electrons. Okay, so that's the structure of a metal. Next question. Look at the diagram above, it's actually on the other page, isn't it? And explain why metals conduct electricity. Why do metals conduct electricity? Well, to answer that, we have to remember what a current of electricity is. A current of electricity is a flow of charged particles. Okay, so what are the charged particles going to be that can flow? They can either be electrons, okay, or they can be ions. Okay, so going back to this diagram here, you may say to yourself, well, it's got both. It's got ions and electrons, so it does have both. Of course, it has positive metal ions surrounded by a sea of delocalized electrons. But metals are solids at room temperatures. They've got high melting points. So these ions cannot move. Okay, they cannot move. So that's not going to be what makes it possible for metals to conduct electricity. What there are these delocalized electrons. Now, delocalized means free to move. So there are free electrons that can move. So metals will conduct electricity. Okay, so look at the diagram above. Explain why metals conduct electricity. Metals have delocalized electrons. Delocalized electrons are free to move. Metals, therefore, conduct electricity. Okay, so this last bit here, why do metals bend without breaking? Okay, well, it's back to this structure again, isn't it? It's of these positive metal ions. Okay, I'm not going to draw the delocalized electrons this time. I'm just going to draw the metal ions. Roughly all the same size if we can. Takes a little bit of time to draw these out, doesn't it? Okay, now, if we were to hit that with a hammer, let's do another row or two. What's going to happen is, okay, these metal ions, because they're all the same size, okay, what they can do is they can slide, they can move along. So let's just imagine we have a hammer that's an atomic scale hammer. Now that's obviously complete and utter nonsense. But let's just imagine it for 1 second. So here's my hammer, okay? And this is just imagine it's an atomic scale hammer, okay? And that hammer we're going to hit that row there, okay, with this hammer. So that's before we hit it. So after we've hit it, if the hammer were that small, and the hammer clearly isn't that small, but let's just imagine. Okay. Then, we've got these first 2 rows still exactly where they were. Okay, but now the hammer has hit this row here, so where those ions were, all that's happened is they're going to slide along. They slide along. So the metal has been deformed. And that one row can slide. In other words, the metal can bend. Okay, the ions that are hit slide along. Okay, so let's try and explain that a little bit. Okay, in metals, if a force is applied, the ions, the metal ions, can slide past each other. This is why metals bend without breaking. Now, you'll probably, if you do separate chemistry, you'll do this again, and you'll do something called alloys. And alloy is a mixture of metals. Now, alloys are much stronger than pure metals, because when you have a mixture of metals, the ions are different sizes, and the different size ions lock these rows together, and so they don't slide anywhere near as easily, making alloys much stronger. But as I say, that's triple chemistry, and you'll do that later on. Anyway, that's metallic bonding.